So today is S9, so it's the 10th seminar, but for the mathematics, theory this is the ninth seminar, and today's topic I put here is algebraical treatise. I'll be talking about the development of algebra, but algebra is such a simple and popular topic that almost all of us know about this algebraical uh, algebra as a mathematics. But there are some historical uh, archives and all these things which I have assembled here so that you will be able to get some insight how algebra uh, has developed. So that's why I called today's seminar as algebraical treatise. First of all, we'll start with two quotes. One was by E.W.L. Glaser, 1948-1928, English mathematician. He said that I am sure that no subject loses more than mathematics by any attempts to dissociate it from its history. So history of mathematics is very important, as told by this English mathematician Glaser. And another is from Peter Kathmandu, Erasmus GL, 1887. They are from the 19th century mathematician, 1960s. Dutch historian. He is not a mathematician. He is a Dutch historian. He said that one can convince history as an argument without end. So my seminar also will go without end. And now, since we are talking about algebra, let's see how some of the big mathematicians has defined algebra. So what is algebra? As for Colin McLaren, Colin McLaren, Scottish mathematician, 1698-1746, wrote in his 1748 algebra text. He wrote that algebra is a general method of computation by certain signs and symbols which has been contrived for this purpose and found convenient. It is called an universal arithmetic. So algebra is not totally different from arithmetic. So it's an universal arithmetic and processed by operations and rules similar to those in common arithmetic. The four simple rules of arithmetic, founded upon the sum in the same principle. So that's how this Scottish mathematician Colin McLaren has defined algebra. And one very prominent mathematician, Leonard Euler, about which we have talked last time, in his own algebra textbook, which he wrote in 1770, he wrote that algebra has been defined the science which teaches how to determine unknown quantities by means of those that are known. So very simple definition by this very big mathematician, Leonard Euler. He has written in his book, algebra textbook, in 1770. Sometimes algebra is defined as generalized arithmetic, as has been quoted here in the earlier slide, and covers a wide varieties of topics. What are the wide varieties? Some of the wide varieties of topics are they include the arithmetic of sign numbers, solution of linear equation, which we are very familiar with, quadratic equation, which we are familiar with, and system of linear and quadratic equation, and the manipulation of polynomials, including factoring and rules of exponents. So it seems that algebra is very simple. It's generalized arithmetic only. We are so familiar with arithmetic that when we generalize it turns into a algebra. The text might also cover, that text of algebra may also cover matrices, we know that, function and graphs, conic sections, and other topics. And of course, if you go to an abstract algebra, nowadays we learn, when you go to master's program, we learn more on abstract algebra. Yes. You will find many other topics, including groups, rings, fields. So evidently, algebra today covers a lot of ground. So now, algebra is not what we used to have in our school time. Now it's a very broad branch of mathematics. The word algebra is derived from the Arabic word al-jabr, and this comes from the treatise written in 820 by the medieval Persian mathematician Muhammad ibn Musa al-Khwarizmi, entitled in Arabic Kitab. So Arabian, some of the words in Nepali are also derived from Arabian words. So Arabian Kitab al-Mukhtar fi Hisab al-Gabar wa Imukalaba, which can be translated as the compendious book on calculation by completing and balancing. So that is the origin of the word algebra. History of algebra is divided. Since today we are talking of history rather than algebra as a mathematics. History of algebra is divided into three sub-stages through the development of symbolism. First is called rhetoric algebra. In rhetoric algebra, all equations are written in full sentences. Okay, there is no symbols, only written in full sentences. So far as you know, rhetoric algebra was first developed by the ancient Babylonians and was developed up to 16th century. Up to 16th century, there was no symbols. All algebraic texts were written in full sentences. Second stage is the syncopated algebra. Syncopated algebra use some symbols, but not as full as symbolic algebra, which will come in the next stage. It is said that syncopated algebra expression first appeared in the book Arithmetica by the ancient Greek mathematician Diphontus, and of course all of us know about this book Diphontus, which is a very famous book about which I have shown the cover page some time back. And another is Indian Brahma Spruta Siddhanta by the ancient Indian mathematician Brahmagupta, 598-670. When I write this symbol C, it means that Siraks, there's some Siraka, sometimes they write it. It means that the exact date is not known. Approximate is 598 to 670. And the third one is symbolic algebra. The full symbolism can be seen in the works of the French mathematician René Descartes. René Descartes we know very much. 1596, 1650. So it came in 17th century. I will say that 1596 is close to 17th century. All the steps of symbolic algebra was taken by Moroccan mathematician Ibn Alban al-Maraqsui, 1256, 1312, and another mathematician Andalusian Matematio of Olua Masan. This is all Spanish. He is a Spanish mathematician, looks like Arabian, 1412 to 1486. So these are the three stages how algebra has developed, from rhetoric, symbolic algebra. Now we'll look in detail some of the history of algebra. The earliest algebra ideas which relate to the 18th century definition by Euler and Maclaurin, about which we have talked earlier in the earlier slides, comes from Mesopotamia, starting from 4,000 years ago. Mesopotamia in mathematics, often called Babylonian mathematics, has two rules. One is accountancy problems. Once you do some account problems, then you have to use algebra. One is accountancy problems, which from the beginning were an important part of bureaucratic system of the earliest Mesopotamian dynasties. Second is a cut and paste geometry. So here I have a historical document. So before Pythagoras, this slide which I am showing is on the left side. You can see the symbol here. This was before Pythagoras. The culture of old Babylonian mathematics. It was discovered not too long back. You can November 12, 2010 and January 20, 2011. Somewhere the study of this, what do you call it? Due to popular demand, before Pythagoras has been extended through January, it has been studied so far. Since the 19th century, thousands of uniform tablets dating to the whole Babylonian period has come to light at various sites in ancient Mesopotamia. So this is a historical slide over here, which translates something like this. Old Babylonian tablets contain problems concerning the digging of trenches. Clay mathematician, 19th, 17th century before Christ. Yale Babylonian collection. So these are collected like this one. The number of this collection is YBC 4663. Photo by Christian Frost, because we have to give this all rights are reserved. So I have to give them the credit. The cuneiform tablets illustrate three major theorems, which I have shown here. Arithmetic exploiting a notation of numbers based entirely on two basic symbols. The sacrable symbols of Nippur, is Nippur an ancient Sumerian settlement, and advanced training. Many of the later problems were much more difficult than any that they would have to deal with in professional sacrable careers, and their solution depend on principle that before the rediscovery of Babylonian tablets were believed to have been discovered by the Greeks of the 16th century before Christ and after that. And in India, as I said, there's a Brahma Spusta Siddhanta regarding the algebraical treatise. So I have put here. There is an English translation of this Brahma Spusta Siddhanta over here. You can see. Now, since I have shown the algebra, the text from India, so I'll talk a bit about algebra in ancient India. Ancient Indian name for algebra is Vijay Ganita. Nowadays, when we teach school level mathematics, in Nepali we also call Bija Ganita, where Bija means elements or analysis, and Ganita stands for the science of calculation. This how. Brahmagupta calls algebra as Kutta Ganita or merely Kutta. So Brahmagupta in his book has written not as Bija Ganita, he has written as more as Kutta or Kutta Ganita. This quadratic equation, solving quadratic equation, also credit goes to Siddharthacharya formula, it is called. It is also known as the quadratic formula or Siddharthacharya method. Some call it Siddharthacharya formula, some call it Siddharthacharya method. Siddharthacharya method is used to find solutions to quadratic equation of the form x squared plus bx plus c is equal to 0, a not equal to 0, that means the quadratic equation, as is given in the form, the one which we have using here, x is equal to minus b plus minus root over b squared minus 4ac by twice a, which is known to every one of us. Later on, I'll show how this formula has been derived by Siddhartha. And in Arabian countries, Al-Khwarizmi's identity and quadratic formula. So in Arab also, this quadratic equation has been solved, and they have this quadratic formula. The quadratic formula is a main tool for understanding quadratic relation. It is based on Al-Khwarizmi's technique of completing the square. His completing the square technique lies on the heart of a beautiful formula that we call Khwarizmi's identity. I'll briefly show it over here. Quadratic equation solved by the Babylonians. The Babylonians were solving quadratic equations as early as 2000 BC. It's a very old mathematics. Their method of solution was different from ours and was expressed verbally because there were no symbols. Of course, nowadays we can write that verbally in the symbols. It was expressed verbally as a series of steps without proof, of course. So, for example, how the Babylonians did this solution of quadratic equation, I'll show in a small example. Let the quadratic equation be x squared minus twice x minus I is equal to 0. Step 1. Take the constant term on the other side, factor the left hand side. So what if you do that, you will have x minus 2, you can take common from x squared minus twice x, and I minus I we have taken to the right hand side. Put a equal to the average, put a small a equal to the average of these terms, that is put a is equal to x minus 1. Then x will be a plus 2, x minus 2 will be a minus 1, and so on. Substituting and solving for using the difference of squares identity, we will come to x minus 2 equal to 8. We have to write in terms of a as a plus 1, a minus 1 is 8. And we know that a plus 1, a minus 1 can be squared, a squared minus I is equal to 9, 8, and a is equal to 9, since a is equal to 9, a is equal to 3, and so putting the value of a into the a is equal to x minus 8, you get a value solution as x is equal to 4. Now the Babylonians did not use negative numbers, so then the only solution for them is a equal to 3, and we have the solution x is equal to 4. So this is the way how Babylon has solved the quadratic equation. Now we use directly the formula. The first known occurrence of the quadratic equation in Egyptian mathematics occurs in the Berlin papyrus, that is written in the paper, papyrus paper found in Berlin, dating from the Middle Kingdom of Egypt, 2160 to 1700 before Christ. For example, to divide 100 squares measures into 2 squares, so that the size of one of the squares shall be 3/4 of the size of the others. Then if you write it in mathematical terms nowadays, if you translate into modern notation, this problem requires to be solved simultaneous equation x squared plus y is equal to 100 and y is equal to 3/4 of x. This give the solution on a sequence of unexplained steps, which basically uses the idea of proportion. So the Greek also solved quadratic equation, but used graphical geometrical method to do so. And there is another example in Euclid's book 2 of Euclid, proposition 11, solve the quadratic equation x squared plus x squared is equal to a squared geometrically. The method used was basically a form of completing the square. In most of the cases, quadratic equations were solved by completing the square. In later books in the elements, for example, proposition 11 in book 4 of this elements, Euclid gave geometrical construction equivalent to solving a general quadratic equation. So, as I showed in the previous cases also, previous slides also, so they were using more of geometry to solve algebra. There is no algebraic solution to this problem. Now, coming back to India, the quadratic equations of the Indians, throughout antiquity, various rules were given for special cases of type of quadratic equation. For different quadratic equations, they have different rules. The so-called Hindu rule was first given by Sridhara in about 1025. So this slide, this slope, which I am written for here, when I was this mathematics students at Soviet Union back in 66, 72, somewhere in 69, Nepali, he had Acharya in Sanskrit, and he was taking astronomy in the Moscow State University. So he invited me, knowing that I am a student of mathematics. He invited me to his room, the hostel room, and we sat over here. Then he recited this poem to me. Taturahat varga samay rupe pache toyam gunayeta objectam varna gure yukte pacho tato mulam taturareva quadratic and all these things. So he said that this is the rule how the Indians solve the quadratic equation. He tried to explain it from the Sanskrit version, but it was not very easy for me. Now I'll translate it for you, since I am now able to do that. Question is, multiply both sides of the equation by a number equal to 4 times the coefficients of the square added to then a number equal to the squares of the original coefficients of the unknown quantity. For example, 4a square x square plus 4ax plus b, 4a is equal to 0. Multiply by 4a. You see, here I have 4a, that is why I have 4a. So multiply 4a, 4a square plus 4ab. So this will be, and add also constant terms, b square, both sides. So here this b square and b square is added. And after very simple simplification, so you can, this 4ac will go back, this will come over here, it will be complete square. So complete square, twice ax plus b square will do b square minus 4a square, this is b square, I take this 4ac on the side. Then we have twice ax plus b whole square is equal to, what we hear b square plus 4ac, we put on the root d and put it square. This d nowadays is called discriminant, it is b square minus 4ac. So this was how the quadratic equation solved by the Indians. So once we have square and if square, we can take out the square, then twice x plus b will be root d, because once we take square we have to plus minus, and we'll have plus minus root square b square, and now taking minus b on the other side and dividing by ax, we have this twice a, we have the value of x minus b plus minus root square b square minus 4ac by twice a. And so it is known as Siddhiracharya Sutra. So the student who was taking astronomy at People's Friendship University, at Moscow State University, I was in the State University, and then he told this spoke to me. Nowadays, I have already translated, and he is Kathmandu. If you go to, nowadays it's not functional, but in the exhibition route. Besides exhibition, there is the Sanskrit campus, okay, Valmiki campus. On the top of the Valmiki campus, coming back from Moscow, he has put down the first astronomical telescope at Valmiki campus. So he has told me about this Siddhartha Sutra over here. Yeah, I have a photo of Siddhartha also. So this is Siddhartha, Indian mathematician, born in 870 C and died in 330 C. Okay, he was the one who separated algebra from arithmetic. It is said like this, the Indian mathematician. Now, since we have talked a bit of mathematics, then we have to, without theorem, there is no mathematics. So, fundamental theorem of algebra. In 1799, at the age of 22, Gauss proved the fundamental theorem of algebra, which states that every non-constant single variable polynomial over the complex number has at least one root. So this is known as the fundamental theorem of algebra. In algebra, the theory of equations is the study of algebraic equations, also called polynomial equations, which are equations defined by a polynomial. Main problem of the theory of equation was to know when an algebraic equation has an algebraic solution. And this problem was solved by the theory of equation was solved by this mathematician known as, here I have portrait of Galois. This portrait taken at the age of 15. There was no photography at the time because he was born on 25 October 1811 in France, and he died on 31st May 1832, age 20. So this was one of the youngest mathematician, prominent mathematician. So he lived only for 20 years. If he could live for longer years, he could have done many other things. So let's quickly look at this Galois. This problem was the theory of equation was completely solved in 1833 by Galois by introducing what is now called Galois theory. It was Galois who was the first to use the word group, making him among the founders of the branches of algebra known as group theory. What is Galois theory? Galois' most significant contribution to mathematics is the development of Galois theory. It shows that he realized that algebraic solution to a polynomial equation is related with the structure of a group of permutation association with the roots of the polynomial. Galois group of the polynomials, that is called. He found that an equation could be solved in radicals if one can find a series of subgroups of its Galois group, each one normal to its successor with abelian quotient. Now you see, now I have in this word another mathematician abelian, or this Galois group is solvable. This proved to be a fertile approach, which later mathematicians adopted to many other fields of mathematics besides the theory of equation, to which Galois originally applied it. And indication of this Galois, in April 1829, Galois had his first mathematics paper published on continued fractions in the Annals de Mathematics. That was the only mathematical paper in the 19th century. On 25 May and 1st June, he submitted articles on the algebraic solutions of equations to Academy of Sciences in France. He passed, receiving his degree on 29 December 1829. He passed, he died. The final days of this Galois is very controversial. On the 15th of June 1831, Galois was tried for threatening the king's life. He was arrested on Bastille Day, that is France Republic Day of that time, 1831, and spent the next 8 months in prison for thwarting authority and imprisoned at Saint Pelage. He was released on April 29, 1832. During his imprisonment, he continued developing his mathematical ideas. Even in the prison, he was doing mathematics. On 29 May 1983, Galois edited his manuscript and wrote a summary of his discovery in a letter to his friend Augustin Chevalier. He writes that, "My dear friend, I have analyzed several new ideas, one concerning the theory of equations, the other integral functions. In the theory of equations, I have studied as to in which cases the equations are solvable by radicals. You will get this later printed in the review encyclopedia. I have often dared in my life to advance propositions about which I was not sure, but all that I have written down has been in my mind for over an year, and it would not be too much in my interest to make mistakes so that one suspects me of having announced theorems of which I could not have a complete proof. You make a public request to Jacobi and Gauss to give their opinion, and not as to the truth, but as to the importance of these theorems. After this, I hope there will be people who will profit by deciphering all this mess. I embrace your efficiency. So Gallus wrote this on 29 May 1832, and this is notes from Gallus' last page before his death, and his death at the age of 20 is a very tragedy, the final days. On the morning of May 30, 1832, this was on 29 May. Now I am talking of 30 May, next year, 1832, an unidentified man found Gallus, one of his history's greatest mathematicians, lying on the ground in a wooden area in Paris. He had been shot once in his stomach during a duel, because at the time there were a lot of cases of this duel fighting, and died in Cochin hospital the next day. So he died on May 2. Gallus' fatal, this is a sketch about Gallus' fatal duel took place on May 30, 1832. So somebody was shooting him, and there are some evidences about that. The true motive behind the duel will most likely remain forever obscure. The most likely reason is he was weary of his life because of his unhappy love affairs. We don't know the lady with which he has loved. The other reason may be his fruitless efforts for gaining recognition for his mathematical work, his financial and work situation, and he finished up a blind alley in a politics as well. So his duel was like a stage suicide. It is still not clear who the other dueller was, or that is who shoot him, the supposed political friends. So he requested his friend to shoot him, and it was just like a suicide, stage suicide. Early in the morning of May 30, 1833, he was shot in the abdomen and died the following day. So this is the grave of Gallus in France. Unfortunately, I have not visited this place, though I have been to Paris in France so many times. His last words to his brother Alfred were, "Don't cry, Alfred. I need all my courage to die at 20." This is the Everest Gallus at Montparnasse Cemetery, Paris. If I go to Paris again, I'll definitely visit it. I was in Paris only in last days of July 2019 with my wife, but I didn't know about it. Now, when I was making the lectures, this seminars, I got this photo. So he was such a strange person. He was only at the age of 1920. On 9 June 1831, a notice with the following content was published in a local newspaper in France. From January 18, every Thursday, Evariste Gallus is starting a public lecture of higher algebra course in the bookstore of Mr. Caio Sorbanos, that is at his Sorbonne Street, house number 5. So he made a public lecture on higher algebra. Maybe people don't understand algebra, but he did such a alarming thing. It was unheard boldness from a pupil against the teacher. He was a pupil of Taylor and all these things. According to the eyewitness, the first lecture was attended by 30 listeners. The third lecture was attended by more than 10 people here. Now you see how the size of the listeners has come down. The third and the last one was attended by just 4 people. So it was so difficult. The Gallus lecture was very complicated. So most of them, they didn't understand that level of advanced algebra. So quickly at the Gallus mathematical work. There are 4 main papers in Gallus mathematical work in a number of smaller and less important attempts. The first to be published was Sur la théorie des nombres, which appeared in April 1830 and contains the theory of Gallus field. There are These are analogous of the complex numbers obtained by adjoining the integers modulo a prime number p, a root of an irreducible polynomial congruence modulo p. The paper contains proof most of the basic features of what later became the theory of finite fields. In a letter to Cheverell, about which I have talked earlier, written on the eve of the duel, Gallus mentioned three memoirs. The first, now known as the premier memoir, in a manuscript entitled Sureless Conditions, the resolvable equation for radicals, that means equations which are soluble in radicals. Gallus submitted work on the theory of equations to the Paris Academy on 25 May and 1 June 1829. I have mentioned that in the previous slide. But this is now lost, and it seems quite possible that Gallus withdrew it on the advice of Cauchy, who was the student of Cauchy, to him it has been given to referee in June 1830. In February 1830, he resubmitted his work in competition for the Grand Prix in mathematics, from the Academy of Sciences and Mathematics, France. But his manuscripts were unfortunately and mysteriously lost on the date of Fourier, and the prize was awarded jointly to Abel, the mathematician, posthumously, and also Jacobi. Encouraged to do so by Poisson, he submitted his ideas to the Academy for a third time in January 1831. It is this third submission which was read by the Academy referee, Poisson, at the time, and Lacroix, and rejected on 4 July 1831. That survives as the manuscript of the premier memoir. It's there in the Academy. This is the remarkable work in which he introduced what is now called the Gallus group of an equation and showed how solubility of the equation in terms of radicals would be precisely characterized by a property of the group. It was the premier memoir which turned the theory of equation into what is now called the Gallus theory. The second memoir also exists. Gallus never completed it, however now, nor it is all correct. Nevertheless, it is an exciting document that focuses on aspects of what is now recognized as the theory of groups. Its main theorem is in theoretic language, that every primitive solution permutation a group has degree, a power of a prime number, and may be represented as a group of affine transformation over the prime field Fp. It also contains an incomplete study of two-dimensional linear groups or most of this mathematics he was doing, and he couldn't complete because he died at the age of 20. And his main work, comprising the paper Sur la théorie des numéros, the premier memoir, the second memoir, and the letter to Kavli, was finally published by Liouville in 1846. Gallus' legacy is enormous. His idea led directly to what is now known as abstract algebra. So abstract algebra emerged from the work done by Gallus. So these are some of the letters he has written to his friend, which some of them I have shown. Group theory. Now, it was Gallus who was the first to use the word group, in French groupé, in a sense close to the technical sense that is understood today, and one of the key founders of the branch of the algebra known as group theory. He developed the concept that is today known as the normal subgroups. He also introduced the concept of a finite field, also known as Gallus field in his order. He constructed the general linear group over a prime field, GL, VP, and computed its order. He realized that algebraic solution to a polynomial equation is related to the structure of a group of permutation, which I have told already, associated with roots of polynomial, the Gallus groups of the polynomials. He constructed the projective spatial linear group, PSL 2P. Gallus constructed them as fractional linear transform. Gallus' most significant contribution to mathematics by far is his development of Gallus theory. Now, enough for Gallus, because he was the one who brought this higher algebra or abstract algebra. Now we go to the simpler one. Quadratic equation. In mathematics, a quadratic equation is one which can be expressed. We have talked with quadratic equation. This is quadratic equation. A quadratic equation is one which can be expressed as a quadratic function equaling 0. Quadratic means 4. 4. The general form of quadratic equation is like this: a to the power x4 plus bx cubed plus cx squared plus dx plus c squared. A is equal to 0, not 0. So that is a quadratic equation. The quadratic equation is the highest order of polynomial equation that can be solved by radicals in a general case. So higher than power 4, we can't solve by radicals. That is one where the quotient can take any value. A, B, C, D, we can take any value. In mathematics, quintic, that is power 5. The quadratic equation is one which can be expressed as a quintic function 5 power 5, equal 0. The general form of quintic equation is x5, b x4, c x2, c x square, x plus f is where it is not equal to 0. Solving quintic equation in terms of radicals was a major problem in algebra from the 16th century, when cubic and quadratic equations were solved until the first half of the 19th century. General form of a quintic equation, the impossibility of such a general solution was proved with the Abel-Ruffini theorem. So after power x4, we can't solve the equation, and for x to 5, general solution was impossibility of general solution was proved with the Abel-Ruffini theorem. Theorem is named after Paolo Ruffini, Italian, who made an incomplete proof in 1799, and Niels Henrik Abel. We have talked about Abel earlier also when we were talking about Abel prizes in Norway, who provided a proof in 1824. Now I'll show you. In mathematics, the Abel-Ruffini theorem, also known as Abel's impossibility theorem, said that there is no solution in the radicals to general polynomial equation of degrees 5 or higher with arbitrary coefficients. Here, general means that the coefficients of the equation are viewed and manipulated as indeterminants. So, on the left is the Paolo Ruffini Theoria General, published in 1799, his theory of general equations. And the right is the Abel's proof and essay on the source and meaning of mathematical unsolvability by Peter Pacis, published by MIT in 2003. The book on the right is in myself. It was a book donated to me by Abel himself. So I have a book which is autograph. Algebra was so difficult for our Nepali mathematics that Nepal Mathematics Society then has to have several type of seminars so that we can, our teachers, faculty at the university especially, at my university also wanted to have different conference seminars to improve the teaching of algebra. So such a one of this, so the conference was held, seminar was held also. Well, on April 20, 2015, so Professor Roberts and his wife Sylvia were the main resource person in the inaugural session, which was held in St. Petersburg. Over here, so this is session over here. I think you know several of them. Roberts is here, Sylvia is over here, is here, and so anyway, so it was held in this hillside inauguration, and then the remaining seminars were held in the Central Department of Mathematics. I offered complimentary breakfast for all the resource persons coming from abroad, at the port is also for Nepali, at the Port Resort Nagarkot on April 23, 2015. This Port Resort belongs to my school student, whom I taught in the school level, and it is now managed by the owner is my student. And so I requested him. He said, "So just go and have breakfast, complimentary." So he offered me, and so I could do all these things. That's again, my wife is sitting here, I'm over here, and so just and all the family right here. And so this the manager of this hotel is a mathematician. He's had mathematics at Central Department of Mathematics. So it was very easy for me to organize a complimentary breakfast for the resource person in Nepal. Though the conference was planned till April 26, 2015, it was abruptly stopped at 11:56 a.m. on April 25, near the end of the presentation of the 6th day, when Kathmandu was struck with a massive earthquake of 7.8 magnitude. Thanks to organizers and understanding of the participants and guests from abroad, everyone were safe. So just for historical record. Now, I am not a mathematician. I work more on differential equations. And mechanics. So I was invited as a special guest uh, in this conference over here. So, so it was a third international congress in algebra and combinatorics held in Hong Kong on, on 20th August 2017. So this is the opening ceremony of that conference. So I am the honor guest. You can see here I am the honor guest for this. So I chaired some of the sessions. I didn't have any presentation over there. Okay, this was held in Hong Kong. It was and during this conference, this prominent mathematician L.A. Boko has given a presentation of my life in mathematics 60 years. Actually, this presentation has motivated me to make my first presentation, mathematics my life. So this was a motivation for making that slide earlier. I chaired the sessions and handed over the participants certificate of participation directly. So I was getting some of the sessions here, giving all these certificates. But they also gave me a certificate. It is a third internal conference in algebra and combinatorics. It's called ICAC 2017. Okay. But during that time, there was a typhoon. We were not allowed one morning, we were not allowed to go outside the hotel premises. So you can see it was a big typhoon over there. Then I also visited Hong Kong University. In Hong Kong University, there was a statue. So there was, for me, the side effects of ICAS 2007 was, I prepared, after coming back, I prepared a course on quantum calculus, whether you have heard about it or not. I prepared a course on quantum calculus for MPhil students of Kathmandu University, but I have not taken this, it has not been given to any MPhil students. Nowadays, we don't have MPhil students of Kathmandu University as of now. Quantum calculus is the modern name for the investigation of calculus without limits. So this is a calculus without limits, very strange type of calculus. The quantum calculus, or also known as Q calculus, began with F.S. Jackson in the early 20th century. So my personal, with my wife, the personal experience was, at the personal experience of feeling the strength of Typhoon Hato, it was called Typhoon Hato. The wind speed was greater than 140 kilometers per hour, just you can imagine. Now, that was all for algebra. Now, to make this preparation of the slide, I am showing some of the books on algebra, which is in my library. So I am showing some of the shelves of the library. If you look closer, if I zoom here, look closer, then you can see that there are a lot of books on algebra, calculus, all books are here somewhere. There must be some book on algebra also. Okay, these are memorial books. The Abel book is here. You can see the Abel book is here. The Abel book presented by Abel is here. This book on the upper shelf are all those which have been gifted to me by the author itself. So you can see, I'll show the mathematics books taken out from this shelf over there. These are different shelves in my library, in my study room. Here. Now, one book is called Practical Algebra by John Welfare, William Wheeler. So, Practical Algebra. About this book, I have quoted from the preface of this book. The need for this course is in practical geometrical algebra first became appreciated in the appreciated school of the Ford Motor Company. So it was not in the academic. So it started from a Ford Motor Company, where many of the practical problems occurring in the various departments throughout the plant were sent to the school offer a solution. Although many of the practical problems occurring in industry results in equations of higher order than the second degree, this text includes only those problems which can be computed with a linear or quadratic forms. The book was published in 1940. You can see. Chapters the contents are positive and negative numbers, formulas, fundamental operations, special products and factorizing, fractions, equations, standard formula, exponents, radicals, graphs. Linear system of equation, three unknowns, geometrical problems, ratio and proportion, quadratic equations, radical equations, trigonometry, recurring gear and jam problems, the fourth is making car, and then it is table of trigonometric functions, answers, and index. So these are contents of this book. Another group is, which is instruction, algebra for class 9. Algebra for class 9, about book. Textbook for grade 9 students, advanced study in mathematics. So in Soviet Union, there are normal schools, there are school for advanced study in mathematics. Actually called mathematician, academician Kolmogorov, who started this advanced study in mathematics. And it contains elements of set theory, functions, exponents and roots, equations, inequalities and their system sequences, elements of trigonometry, elements of combinatory and probability theory. Then I have another book called Pripitavane Algebra in Geometry and School. This is about book, Manual for Teachers for Teaching Algebra and Geometry in School. Collection of articles written by experienced teachers and pedagogical experts. And this has, in the context, there are general questions by the methodology in the study of algebra, geometry, and beginnings of analysis. There are 11 articles related with this. Particular solutions, questions of the methodology in the study of the beginning of analysis and geometry. There are 5 articles related to this topic. Questions of methodology in solving problems of the school course of fundament of mathematics and special system of exercise. There are 7 articles related with this in this book. Now, these are books published in Nepal with the encouragement from Raman Sester, and he himself is an author in the right hand side. On the left hand side, Algebra and Geometry by Mohan B. Singh and Y.R. Stapit. Mohan B. Singh passed away a long time ago, but Y.R. Stapit passed away. Because I saw, yeah, he saw only few years back, and because he is relative to us. And another elementary linear algebra with groups and rings by Raman Sester and Santi Bajajchare. It's the honor book, honor grad algebra written by Bhadra and G.P. Thakal. Now, these are Russian books which I studied when I was a master's student, doing my master's in mathematics in Russia. Another is, one is Akuros. This is a Russian English translation of the Russian book. Akuros, by author Akuros, higher algebra, and on the right is linear algebra. These are 2 Russian books which I studied over there. Now I have another book called Linear Algebra. It's a 4th edition over here. Eastern Economy editions. It's a republication, and so it's a bit cheaper version. And this is one of the most important books in algebra. It's algebra by B.L. van der Waerden. It's called Waerden algebra, and anybody who are interested in algebra must read this book. So that was Russian version. I also have an English version. So if you see B.L. Waerden, Algebra 1, Algebra 2, it has 2 parts. The English version, PDF of these 2 volumes can be downloaded free. So I have downloaded this free. You can download it free. You can just type B.L. van der Waerden algebra, and you can. Oh yeah, this is the German translation, 1979. The Bartel Leonard van der Waerden is full name. Bartel Leonard van der Waerden was born in Amsterdam, Netherlands, on February 2, 1993, and died at the age of 92 on January 12, 1996. He lived a very long life in Zurich, Switzerland. So both these cities, Amsterdam, Netherlands, and Zurich, Switzerland, I with my wife visited in end of July 2019. Bartel Leonard van der Waerden was a Dutch mathematician and historian of mathematics and science. So van der Waerden was an extremely bright student, and he was well aware of this fact. He made his presence in class known through bright and sometimes irreverent remarks. Being quick and sharp, he could make life miserable for the poor teachers in front of the blackboard. So it's not a boy, not a student. Bartel Leonard van der made contribution to abstract algebra, combinatorics, history of ancient science, history of modern physics, gravity theory, algebraic geometry, history of astronomy, mathematical statistics, quantum mechanics, analysis, group theory, history of mathematics, number theory, probability, and so on. So he was a very versatile type of mathematician, and more related with history. Van der Waerden's book, A History of Algebra from Al-Khwarizmi to Eminator, appeared in 1985 and provided a personal account of the development of algebra. Starting with Al-Khwarizmi from those treatises, the word algebra, he derived. Van der Waerden traced the development throughout the ages to modern times. In his view, modern algebra began with Galois, as has been mentioned, I have told, which first investigated the structure of fields and groups and showed that these two structures are closely connected. After Galois, the effort of the leading algebraists were mainly directed towards the investigation of structure of rings, fields, algebra, and the like. Van der Waerden traced such investigation up through roughly the middle of 20th century in a discussion that comprises some two-thirds of the book, and that includes some of his own contribution. Only Van der Waerden could have given us this fascinating account. There's an interview by Hugo Champions was held in Zurich at Van der Waerden's home on May 14, 1993, shortly following his 90th birthday. Once we have a celebration of 19th birthday, people come and have interview. So the person told Champions asked him, "Did you begin to write your book on algebra while you were at Groningen?" Waerden answered, "Yes. Then in 1929, I took the position of visiting professor at Göttingen, Germany, and there I met my wife." Then the questioner said that told asked, "This book on the foundation of algebra, modern algebra, 1, volume 1930, was a great success. Did you have many readers right from the beginning?" Then the Waerden answers, "Yes, from the beginning. With my book, The Algebra, it went like this. Artin was supposed to write a book and wanted to write it with me. Having finished the first chapter, I showed it to Artin, the other mathematician, then his friend. Then I sent him the second and asked him about the progress of this part of the book. He hadn't yet done anything. Then he gave up the idea of writing the book with me. Nevertheless, the book is based on the lectures of Artin and Noether." This email Artin, his friend, 1998, 1962 Germany, was one of the leading mathematicians of the 20th century. He is best known for his work on algebraic number theory, contributing largely to class field theory and a new construction of L functions. This Emilie Noether, 1832-1835, also from Germany, was a groundbreaking female mathematician who made many important contributions to abstract algebra. So this is a portrait of a photo of Van der Waerden in making a lecture in Zurich in 1973. So Van der Waerden once told, "None of the three of my children had any interest in mathematics, so he couldn't pursue his children to the sphere of mathematics." So that's enough for today. I think I've had a long discussion over here. Anyway, so we'll continue. That was algebraical treatise, how algebra has developed over there. Many historical events related to development of algebra. So next seminar will be after 1 week on December 24, 2021. It will be yesterday. Throughout the ages. And topics for next seminar is very different type of seminar. How focal works. One part. And other part is mathematical body. So we'll meet after 1 week, and those who are interested can get a PDF version of my S9 algebraical treatise. Okay, thank you very much.
Okay. Well, thank you so much, Bhadra Man sir. So I think so. This was really the interesting the development in algebra. So that is quite interesting, as well as so some of the developments that we are not familiar. I am actually not familiar with because there are so many things that we have to learn. And so sir talked about the very early age where the algebra was developed, and the modern age that so different the development of in algebra that we have been interacting with. So really um interesting talk, sir. So I think so we have participants from Nepal as well as from outside Nepal. So if you have any questions related to Bhadra Man sir's presentation, you can ask.
त्यो
I think
गालाउको लेक्चर जस्तै होला,
also
क्यालेन्डरले चाहिँ कस्तो पब्लिक लेक्चर दियो, इन्ट्रेस्ट हटाएर लास्ट लेक्चर चारजना मात्रै बाँकी भयो
त्यही त नि सर।
सर नमस्कार, म
सर
दीपक
नमस्कार, म
गन। अब
दीपक गन। अब
हजुर
हजुर
यो कस्तो फिडब्याक आइरहेको छ क्या यो आफैलाई नै बोल्दाखेरि। सरले त आज त पुरै संसारै घुमाउनु भयो नि।
आफै संसार घुमेको छ अनि के हुन्छ।
इन्डियादेखि अरबसम्म, अनि फेरि मेसोपोटामिया, अनि त्यसपछि आएर तपाईँले त्यो ग्याल्वाको सबभन्दा त्यो म्याथमेटिक्सको एउटा ट्रेजेडी भन्न पर्ने चाहिँ इभेन्ट, त्यो ग्याल्वाको स्टोरी त 20 years को मान्छे त्यसरी गएर पनि स्टिल आई मिन हि हेज सो मच, हि डिड सो मच भन्ने जस्तो सबै कुरा लिएर आएर एकै ठाउँमा ल्याएर सुनाउनु भयो। त म त त्यही त सुरुमा चाहिँ अब श्रीधरको बीजगणितको कुरा आएपछि सरले अब त्यही बाटोतिर लानुहुन्छ होला भन्ने लागेको थियो। थ्योरी अफ इक्वेसनमा आएर जोडिन्छ होला भन्ने त आई डिडन्ट इभन एक्सपेक्ट। त्यही त ग्याल्वाको लेक्चर जस्तै भयो भन्नुभयो होला। आज सबै एटेन्ड गरेकोमा आई थिङ्क आई फाइन्ड दिस वान इज भेरी युजफुल, भेरी इन्ट्रेस्टिङ। अनि मलाई चाहिँ कस्तो लागेको भने जस्तो यो बारेमा कुरा त पहिला पनि गरियो होला, धनकुमारी म्याम आउँदाखेरि खालि त्यही कुरा गर्नुहुन्छ, हामीले हाम्रै लोकल नलेजलाई पनि लानु पर्यो भनेर। त मलाई चाहिँ के लागेको आज भने जस्तो अस्ति कुरा भएको थियो, जस्तो अहिले यो सुन्दै गर्दाखेरि ओहो मान्छेले पुरा एस्ट्रोनमीदेखि लिएर म्याथमेटिक्स, त्यसपछि त्यसबाट स्लाइडली टच हुने सबै फिल्ड, फिजिक्स, केमिस्ट्री जताततै एउटै मान्छेले त्यत्रो गर्न सकेको छ भने हामीले चाहिँ किन नसक्ने भन्ने जस्तो एउटा त्यो के भन्छ मोटिभेसन आउने क्या यो हिस्टोरीको कुराहरू सुन्दाखेरि चाहिँ। अनि आई थिङ्क त्यही नै हो रिसर्चले अहिलेसम्म भनेको पनि के हो भने यदि हिस्टोरिकल सोर्सबाट यदि विद्यार्थीलाई पढाउन सक्ने हो भने सबभन्दा पहिलो कुरा त्यसले ल्याउने भनेको मोटिभेसन हो। अनि हामीलाई चाहिएको अहिले चाहिँ सबभन्दा मुख्य कुरा भने मोटिभेसन नै हो। विद्यार्थीलाई मोटिभेट गर्न नसकेका कारणले गर्दाखेरि अहिलेको एजुकेसन पछाडि पर्यो भन्ने कुरा। किनभने मेरो अलिअलि लाइन अफ रिसर्च चाहिँ त्यतातिर नै जान्छ, हाउ टु युज हिस्ट्री टु टिच करेन्ट कोर्सेस भन्ने जस्तो होइन। अब त्यो हिसाबमा चाहिँ त्यो टेक्स्ट बुकमा सरले अघि देखाउनु भएको टेक्स्ट बुकहरूमा जुन हिस्टोरिकल सोर्सेसहरू त्यो त्यसको इन्फर्मेसनहरू राख्यो भने जस्तो अहिले हामीलाई सरको कुरा सुन्दै गर्दाखेरि हो हामीले पनि गर्न सकिन्छ है भने जस्तो परे जस्तो विद्यार्थीलाई पनि 20 वर्षकै मान्छेले यत्रो काम गरेको रहेछ भन्ने जस्तो। अरू केही नभए पनि सामान्य नोटहरू जस्तो टेक्स्ट बुक अथरहरूले त्यस्तो राखिदिने भनेदेखि कति फरक पर्थ्यो होला। त्यसले पक्कै पनि त केही न केही चाहिँ नयाँ किसिमको ऊर्जा दिन्थ्यो होला नि विद्यार्थीलाई भन्ने लाग्छ क्या। अब मलाई चाहिँ अब आफू किताब नलेखिने, अब त्यो भएर गफ गर्न सजिलो हुने, आफैले गर्न पऱ्यो त गाह्रो हुन्छ होला। तर एउटा सजेसन, एउटा दिमागमा खेलेको कुरा चाहिँ सरको आज प्रेजेन्टेसन सुन्दै गर्दा, तर होइन त्यो ग्याल्वाको प्रेजेन्टेसन जस्तो भएन मलाई त आज त एकदम आई मिन आई एम भेरी एक्साइटेड टु हियर अल दिस टक। थ्याङ्क यू सर, तपाईँले जताततै पुर्याउनु भयो, धेरै नलेज राख्नुभएको सरले। सरको लाइब्रेरी पनि देख्नु पाइयो, खुसी लाग्यो। थ्याङ्क यू।
Totally agreed with Deepak.
के छ
सर म सुनिरहेको थिएँ, एकदम रमाइलो लाग्यो सर। त्यस्तो ग्याल्वाको मलाई इन्ट्रेस्टिङ लाग्यो सर। मैले तपाईँलाई एउटा इमेल पनि पठाएको छु।
मैले हेरेको छु।
आज मैले अघि भर्खर एकदम इन्ट्रेस्टिङ लाग्यो सर।
उर्मिला म्यामको अलि
स्वर कम छ, बोल्नै गाह्रो। म कानमा राखेर सुनिरहेकोले म अलिअलि सुन्छु
ए सुन्नु भएन
अलिअलि सुन्छु
ए सर सुन्नुहुन्छ
ए हामी सबै बोल्न छोड्यौँ त ओके अरु सर म्यामहरुको केही छ त
बच्चाले के पनि बोलेन आज
सो अब
मैले आफ्नो पालो पुर्याएँ भनेर बोलिनँ अनि मलाई त एकदम त्यो मजा लागिरहेको छ सरले जति कुरा सुनाउनु भयो अब यहाँ पक्कै अरू सर म्यामहरुको नि क्वेशन होला भनेर आई डिडन्ट वान्ट टु टेक सो मच टाइम एनीवे थ्यांक यू सर त्यही हो अब नेक्स्ट विक
देखेको नसुनेको चीज त मैले धेरै चाहिँ नि यो मेरो सेमिनार राखिदिएको छु नि
ए अनि अर्को ठ्याक्कै सरले अहिले भन्दा सम्झे त्यो जुन प्यारिसको ग्याल्वाको त्यो टर्मको कुरा गर्नुभयो द्याट्स माई नेक्स्ट डेस्टिनेसन है म मिल्यो भने 22 मा जाँदैछु अब यो ओमिक्रोनले के हुन्छ म चाहिँ त्यहाँ जाने प्लान म अस्ति 18 मा चाहिँ गएको थियो प्यारिसमा तर आई डिडन्ट नो अबाउट इट अब थाहा भयो नि त सरलाई पनि थाहा रहेन रहेछ अब ठिकै भयो अब सरले त्यो सुनाइदिनु भयो अब चाहिँ यो एउटा जानुपर्ने ठाउँ भन्ने लाग्यो अस्ति त त्यही आइफल टावरको मुनि फोटो खिच्दै नै ठिक्क भयो नि अब त्यता जानुपर्छ
हुन्छ अब हाम्रो चाहिँ अब यो रेकर्डिङ्सहरु छ हैन सो दे आर अल अभाइलेबल अन आवर युट्युब च्यानल त्यसमा पनि गर्नु होला हुन्छ सर आजलाई एन्ड गरौँ होला थ्यांक यू सो मच फर जोइनिङ
अर्को विकको त छ नि अर्कै खालको छ
अब सरले अलिकति यो टेक्नोलोजिकल इनोभेसन र म्याथमेटिक्सको हिस्ट्रीलाई जोड्दै हुनुहुन्छ हैन सर
अनि त्यहाँ त्यो भनेको चाहिँ नि त्यो हाउ गुगल वर्क्स भनेको म्याथमेटिक्स बिहाइन्ड त्यो गुगल हो
डेफिनेटली सर
मतलब सर्च इन्जिन म्याथमेटिक्स बिहाइन्ड सर्च इन्जिन
So mostly like the algorithm को history जस्तो हो सर
algorithm को history होइन त्यो पुरा म्याथमेटिक्स आउँछ त्यहाँ चाहिँ कुन म्याथमेटिक्स को चाहिँ नि टपिकहरु चाहिँ रिलेटेड हुन्छ एउटा चाहिँ सर्च इन्जिन बनाउनलाई भनेर हो म कम्प्युटरको कुरा गर्दै थिएँ व्हाट आर द म्याथमेटिक्स बिहाइन्ड दिस सर्च इन्जिन गुगल जस्तो गुगलमा के म्याथमेटिक्सले त्यहाँ प्ले खेलेको छ भनेर त्यहाँ त्यो देखाउने
इन्ट्रेस्टिङ
अर्को चाहिँ म्याथमेटिक्स भनेको त त्यो ठुलै संसार हो त्यसको चाहिँ नि अब त्यसमा अलि लामो पनि हुन सक्छ एनीवे विल मिट नेक्स्ट विक
साउन्ड्स गुड
थ्यांक यू सो मच
थ्यांक यू एन्ड गुड नाइट गुड मर्निङ उसलाई बच्चालाई गुड मर्निङ भन्यो सबैले गुड नाइट भन्नु
सबैलाई गुड